So let's apply what we've learned. In the sketch at right, a designer has provided the dimensions required to define the nominal sizes of the diameter, which is here, and the length of a cylinder. The designer has specified a plus or minus tolerance of 0.01 inches to both of the nominal sizes. So let's analyze the designer's sketch a little bit. Applying the tolerance to the part's nominal dimensions would result in the cylinder's diameter ranging between a minimum of 0.97, a diameter of 0.97, that would be 0.98 minus 0.01, and a maximum diameter of 0.99, right? So if we've got 0.98 plus or minus 0.01, the largest it can be is 0.99, the smallest diameter it can be is 0.97. If we apply that same thinking to the length of the cylinder, the minimum length of the cylinder would be 1.99, and the maximum length would be 2.01, because we have 2.00 plus or minus 0.01. The shortest would be 1.99, longest would be 2.01. There's a term we use when the cylinder is at its largest diameter. A designer might say that that feature, which is the diameter of that cylinder, is at maximum material condition, or MMC. So when the cylinder is largest, it has the most mass. And that's why it's referred to as maximum material condition. It has the most material in it. When the cylinder is at its smallest diameter, a designer might say that the feature is at least material condition, because there's less material when this cylinder is at its smallest diameter. The length of the cylinder is at MMC, maximum material condition, when it's at its longest, which is 2.01, and it would be at least material condition when it's at its shortest, which would be 1.99. A definition of maximum material condition is the condition of a feature when it contains the greatest amount of material. A definition of least material condition is the condition of a feature when it contains the least amount of material. So understanding the term maximum material condition and least material condition, and referring to them even as MMC and LMC, these are very important terms for designers. Now, let's analyze this part over here. So we have a block that has a hole drilled through it, and the diameter of that hole is 1.00, and it has a tolerance of plus or minus 0.01. The center of that hole is located from this edge here, 1.00 plus or minus 0.01. The center of the hole is located from this edge, 1.00 plus or minus 0.01. We might say that this edge down here and the edge on the opposite side, because we are locating the center of the hole from those surfaces, we might say that those are datum features. A datum feature is an element like an edge, a plane, a point, an axis or a hole, or other geometric feature that serves as a reference for defining the geometry of an object. Okay, so if we're locating the center of this part from these surfaces here, then those surfaces are datum features. So we've already said the designer has noted a tolerance of plus or minus 0.01 that's going to be applied to each nominal dimension in the sketch. So let's talk about the maximum material condition of the hole. Subtracting the minus tolerance from the hole's nominal value will define its MMC. The hole's nominal size is 1, and the minus tolerance is minus 0.01. So in this case, the MMC for the hole's diameter is 0.99. Now that seems weird, because when we had the cylinder, when the cylinder was the largest diameter, we said it was at MMC. But it's the opposite for a hole. When this hole is at its smallest diameter, right, which would be 0.99, it's at MMC. Because when the hole is smaller, the part has more material left behind. If we calculate the least material condition, it's the opposite of that. If we make a larger hole, which would be 1.01 with this tolerance here, so we have a larger hole, we've actually removed more material from our part. So we would say when this hole is larger, that this feature is at least material condition. All right, so we've defined a datum feature as being a surface that we're taking measurements from. It could also be a center axis, or it could be a point or a plane or something like that. But I want to kind of distinguish it from a datum. In geometric dimensioning and tolerancing terms, a datum is a theoretically ideal or perfect line, point, axis, or surface from which tolerances are referenced from. Datums may even be simulated by a near perfect granite surface plate. Like if you put this part on a perfect, near perfect anyway, granite surface plate, and then you measured from the top of the plate to the center of the hole, and you put another plate on this side and measured from the surface of the plate to the center of the hole, that would be an example of using a datum. So the datum often lies off of your part, and sometimes when we use precision measurement equipment like a coordinate measurement machine, the datum is actually simulated or virtual. But when we're measuring from the actual side of our part, we call that a datum feature, while a datum is a theoretically more perfect plane or line or point that we're measuring from that does not lie on the part. All right, so let's go back and look at these dimensions here that locate the center of that hole. Now, it's 1.00 on both, plus or minus 0.01, and we're measuring from our datum edge, which we called our datum feature, right? So what that means is the center of this hole along this axis, the y-axis, the center of that hole could be as close to this edge as 0.99 and as far away from this edge as 1.01. If it were perfectly at 1, it would be at its true position. When we measure from this datum feature, the center of the hole could be as close to this side as 0.99 inches, or it could be as far away from that hole as 1.01. If we draw a box to represent the sides that go from 0.99 to 101 on this axis, the x-axis, and if we draw that box from 0.99 to 101 on the y-axis, what we see is what's called a square tolerance zone. And the reality is that the center axis of this hole right here can hit anywhere inside that box, even on the corners of that box, and the location of the hole will still pass inspection. So the true size of our tolerance zone here, our square tolerance zone, is 0.02 by 0.02. because it's 1/100th of an inch on either side from where our true perfect location of the hole would be. So, sometimes you go into this thinking the location of that hole can only be 1/100th of an inch off, but actually the location of that hole can vary from left to right and up and down within 2/100ths of an inch. And remember, we would also refer to that as 20 thou. When the part is inspected, the inspector's measurements will be made from the same datum edges and datum features that are defined in the technical drawing. So it's important that you dimension from the same datum edges or datum features as the designer did. So, as I said, we call this a square tolerance zone. Square tolerance zones are often considered a shortcoming of coordinate dimensioning, and this is what we're doing right here. This is called coordinate dimensioning. Geometric dimensioning and tolerancing, which I spoke about earlier, allow designers to avoid these square tolerance zones. So as I said, GD&T is something that's worth looking into if you intend to become a mechanical designer. All right, so we're still applying what we learned, and this is the last part of it. So let's see, could we calculate a fit between two parts? So if we look at our cylinder here and we look at our nominal sizes, we can figure out what's the largest diameter and the smallest diameter this cylinder can ever be. We can do the same thing for our hole right up here. We know the largest the diameter could ever be is 1.01 and the smallest it could ever be is 0.99. The designer would be looking at those same dimensions and thinking, okay, am I assured that this cylinder will fit through that hole there if this cylinder is manufactured at its greatest diameter and if this hole is manufactured at its smallest diameter? And remember, the greatest diameter of this is called the MMC, the maximum material condition, and the smallest diameter of the hole is called the MMC, the maximum material condition. So let's look at the best case scenario for assembly. Best case would be when it's easiest to fit the cylinder into the hole. So if they manufactured the cylinder at its least material condition or smallest allowable diameter, that would be 0.97. And if they manufactured the hole at its largest diameter, which is also its least material condition of 1.01, then the hole would actually be 0.04 inches larger than the diameter of the cylinder. So the cylinder would easily fit because it has 0.04 of an inch or 40 thou of an inch of clearance. All right, this clearance can be referred to as an allowance. Now let's look at the worst case scenario for assembly. The worst case exists if the cylinder here is manufactured at its MMC, which would be its largest size, which would be 0.99, right? And if the hole were manufactured at its MMC, which would be its smallest diameter, which would also be 0.99. So now we have a cylinder at 0.99 and we have a hole at 0.99. Would those fit together? Well, in theory, they should fit. But because they're the same size, the cylinder would have to be exactly aligned to the hole, and it would not be easy necessarily to fit the cylinder through that hole. So when we look at it like that, we would say that's our worst case scenario for assembly. Our best case is where we have a lot of allowance or a lot of clearance in that. But best case is relative. What if the 0.04 was too loose so that the designer looked at that and said, well, that will clear that hole really easily, but then it's going to rattle around and it's going to make noise, or it's not going to stay in place. It's going to vibrate. So it's possible that even the best case scenario is not really the best. It's just that it's easier to assemble them at the best case. In that case, the designer might think about the nominal diameter here or the nominal diameter here, or even think about changing their tolerances so they could achieve less of an allowance in here or more of a clearance down here. It just depends on the function of the parts. So if the designer desired a looser fit at MMC, they might take this dimension here and reduce it to 0.97. Or the nominal size here could be enlarged to 101. Either of these would result in having more clearance between the part, regardless of whether the part was made at MMC or not, okay? Because if this was at 0.97, if our nominal size was at 0.97, then the largest this could ever be would be 0.99, right? And then if our hole over here we're at 1.01 plus or minus 0.01, then the smallest the hole would ever be is 1.00. So if this is 0.99 and this is 1.00, then we would have 1/100th of an inch of clearance on those every time. So allowance is the minimum clearance or maximum interference between mating parts. So after a part is manufactured, it's important to confirm that all its features fall within the allowable size limits defined by the dimensions and the tolerances noted on the drawing. This step in the manufacturing cycle may be performed by a quality control or a QC inspector using precise measuring equipment called metrology equipment to determine the actual size of the part. The QC inspector compares the actual size of the part, which is the part that the features measure at, to the part the dimensions say the part should be within its tolerances. Does that make sense? So when the part is manufactured, we measure it, and when we measure it, we find out what its actual size is, and we compare that to the size listed on the drawing and applied with the tolerances. Parts that measure within the allowable size limits will pass the QC inspection, while parts that measure outside the limits are rejected. So actual size refers to the measured size or location of a feature of a manufactured part. This is the size that determines whether or not the part passes a quality control inspection. So, in summary, do you think designers and manufacturers like tolerances? The answer is that designers and manufacturers both like tolerances for the following reasons. Clearly defining the precision of parts on drawings that are going to be used for the manufacture of the parts avoids problems and disputes later. The clearer the drawings are, the less likely there's going to be a problem or a dispute later. When the features of a part are manufactured within the dimensions and tolerances specified on their engineering drawings, the engineer or designer can be confident the part meets their design intent with regard to fit, form, and function. If an outside manufacturer is hired to make the parts, and the parts are not within the dimensions, tolerances, and specifications shown on the drawings, the organization may not be obligated to purchase the parts. On the other hand, when the parts are manufactured within the dimensions and tolerance specified on the engineering drawings that are sent to the manufacturer, the organization that ordered the parts is obligated to purchase the parts because they are within the specifications. So when the manufacturer makes the parts within the dimensions and tolerances specified on the drawings, then she can be sure that the organization that ordered the parts will pay for them because they are within the specification. All right? So designers and manufacturers both like tolerances. Designers like them because when their parts are made within the tolerance, the design intent for the part is met. Manufacturers like them because when they build something and it measures within the tolerance, then they know they're going to get paid for making it. So that's the end of the video on tolerancing. And so if we were doing this live, I would open up the floor for questions. I'm sure there's going to be some. But good luck with your tolerancing. It's a really fascinating part of machine design.